Thyristor types. Thyristors are manufactured almost exclusively by diffusion. Thyristors are switching devices. The anode current requires a finite time to propagate to the whole area of the junction from the point near the gate. When the gate signal is initiated for turn on the thyristor, the manufacturers uses various gate structures to control di by dt, turn on time and turn off time. So depending upon a physical construction and turn on turn off behavior, thyristors are classified as, first one, phase control thyristors known as SCR, silicon control rectifiers. Second one, fast switching thyristors. Third, gate turn off thyristor, that is GTOs. Bidirectional Triode Thyristor. TRIACs. Reverse conducting thyristors, RCTs. Static induction thyristor. Sixth, light activated silicon controlled rectifiers, lasers. FET controlled thyristor. Ninth one, MOS controlled thyristors, MCTs. Let us see one by one. First one, the phase control thyristor. These are generally operated at a line frequency and is turned off by natural commutation. Commutation is a process of turning off the thyristor. This is again two types, that is natural commutation and forced commutation. And forced commutation is again divided into 7 types depending upon the devices and the combination of the parameters involved in the circuit. That we'll see in later videos. Now, at the turn off time, it is TQ, it is 5200 microseconds. This is most suited for low speed switching applications and known as converter thyristor, also known as SCR, that is silicon rectifier controlled, since the thyristor is basically a silicon made control device. Now, the unstable voltage VT for this type of thyristor is typically 1.15 volts for 600 volts device and 2.5 volts for 4000 volts device, and it is typically near about 1.25 volts for 1200 volts 5500 amps device. Fast switching thyristors used in high speed switching applications, and here a forced commutation is used. These are having fast turn off time, generally it is 5 to 50 microseconds. These are known as inverter thyristors. For this VT is near about 1.7 volts for 1800 volts 2200 amps device. Fast turn off time varies between 3 to 5 microseconds, so commonly known as asymmetrical thyristors, ASCRs. In the phase control rectifier, that dV by dt 1000 volts per microseconds and di by dt 500 amps per microseconds, which simplifies the circuit design by reducing or minimizing di by dt limiting inductor and dV by dt protection circuit. Whereas in this case, it is 1000 volts per microseconds and 1000 amps per microseconds. Gate turn off thyristors. A GTO is a latching device and can be built with current and voltage ratings similar to SCRs. A GTO is turned on by applying a short positive pulse and turned off by short negative pulse to its gates. The GTO has the advantage over SCRs. Those are, the first one, it eliminates commutation components in forced commutation, resulting in reduction in cost, weight and volume. Second, a reduction in acoustic and electromagnetic noise due to the elimination of commutation chokes. Third one, faster turn off permitting high switching frequencies. Fourth one, improved efficiency of a converter. These are the advantages of GTO over SCRs. The advantages of GTOs over transistors in low power applications. First one, higher blocking voltage capability. Second, high ratio of controllable current to average current. Third one, high ratio of surge current to average current, typically 10:1. Fourth one, high on-state gain anode current to gate current, typically 600. Fifth one, pulse gate signal of short duration. Under such condition, the GTO goes into deeper saturation due to regenerative action. On the other hand, a bipolar transistor, that is BJT, tends to come out of the saturation. The GTO have low gain turn off, so typically 6, and requires relatively high negative current pulse to turn off. It has higher on-state voltage than that of SCR. VT of the GTO is 3.4 volts for 1200 volts, 550 amps. Controllable peak on-state current, that is ITGQ. ITGQ is the controllable peak on-state current which can be turned off by gate control. The off-stage voltage is reapplied immediately after turn off, and reapplied dV by dt is only limited by the snubber capacitance. Once the GTO is turned off, the load current IL, which is diverted to and charges the snubber capacitance, determines dV by dt is equals to load current divided by snubber's capacitance. Bidirectional triode transistor or TRIAC. TRIAC can conduct in both directions. It is normally used in AC phase controllers like AC voltage regulators. It can be considered as two SCRs connected in anti-parallel with common gate connection. And the equivalent TRIAC circuit is shown like this. This is the symbol of TRIAC, and these are the VI characteristics of a TRIAC. So TRIAC is a bidirectional device. So we are not mentioning here that anode and cathode, but we are mentioning this with MT1 and MT2. If MT2 is positive when compared with MT1, then the TRIAC can be turned on using positive gate signal between gate and MT1. Then the TRIAC is going to conduct in first quadrant. If MT2 is negative with respect to MT1, TRIAC is turned on by a negative gate signal between gate and MT1. Then the TRIAC is going to operate in the third quadrant. And it is not necessary to have both polarities of gate signals. TRIAC can be turned on with either positive or negative gate signal. In practice, the sensitivity varies from one quadrant to another. There is quadrant 1 to quadrant 3.